Hello, my name is Noah, and I'll be giving a presentation on a literature survey over dynamic Bayesian networks. In this course, we went over Bayesian networks and hidden Markov models, which are a type of dynamic Bayesian network. But today I will go over the larger class of dynamic Bayesian networks, or DBNs. A DBN is a Bayesian network that relates variables to each other over adjacent time steps, called time slices, so they can capture the evolution of random variables over a series of instances. The value of a variable can be calculated using internal regressors and the value from the previous time slice, which can be modeled by the equation shown on this slide. DBNs change the static nature of Bayesian networks to one of motive force, giving the user the ability to watch and update the system as time progresses, leading to the ability of prediction. The diagram below shows a representation of a time slice approach, where the time slices represent snapshots of a dynamic temporal sequence. A comparison that can be made between Bayesian networks and DBNs is over interslice connections and intraslice connections. The intraslice connections of DBNs are the same as those of Bayesian networks, where we have the same edges, nodes, and probabilities. The difference comes from the existence of interslice connections for DBNs due to the added dimension of time that requires using conditional probability tables instead of distributions and a modification to the inference method. Any individual step of a DBN can be converted to a BN through a process called unrolling. The main use of unrolling is to understand the structure of a DBN, but DBN predictions are done through other inference methods because unrolling performs poorly when increasing the number of time steps, since when you have n time steps, there's no guarantee that the complexity of inference scales linearly with n. This will require large amounts of memory that is a function of n, and n itself may be unknown. Instead, what can be used is an interface algorithm, an algorithm that reduces inference by exploiting repeated structure in the DBN through a forward pass that computes joint probability distributions for all time steps shown below. The interface algorithm calculates the random variable z using junction trees to compute the marginal probabilities. This overcomes the drawbacks of unrolling the system by scaling linearly with a number of time slices, requiring only memory of the previous time step. For the rest of the presentation, I will go over the main types of DBNs and their applications. The first major DBN is the hidden Markov model, but I will not go over its derivation since this was covered in the course, and I will go over some of the main applications instead. One application of hidden Markov model is in degradation models. Degradation models have been very uncertain due to limited information on environmental, loading, and material characteristics, which has led to the emergence of hidden Markov models as robust and efficient solutions because they allow you to learn about the quality of the material by observing the degradation. The challenge of using hidden Markov models is to find features that are not due to attributes that are uncorrelated with a degradation condition, but this can be overcome using nuisance attribute projections. This method filters out nuisances in classifiers to clear the feature space of these unwanted, uncorrelated attributes. Another application of hidden Markov models is in audio-visual speech recognition. Existing audio-visual integration techniques use decision fusion to achieve observation sequence, such as a hidden Markov model variant called the multi-stream hidden Markov model. Multi-stream hidden Markov models allows for independent computation of audio and visual sequences, allowing the weights of audio and visual contribution likelihood to be applied to the overall likelihood. However, the multi-stream method also has the drawback of being unable to describe the asynchrony between audio and visual recognition. So this led to the application of a new method in the field, the coupled hidden Markov model, which has allowed for the backbone nodes to interact with each other, audio and visual, instead of acting independently. The performance accuracy of these methods are shown in the table below, in the third row and the final row, respectively, along with other variants of the hidden Markov model, but we see that these are the best two for all levels of SNR. Another type of DBN is the Kalman filter. The most basic Kalman filter is the linear Kalman filter, or LKF, which is an algorithm that estimates states based on linear dynamical systems with stochastic estimation of a linear system using noisy measurements. First, a state is estimated via a linear model from time step t to time step t plus 1, called the time update step. Then an external sensor provides an estimate for the state with uncertainty called measurement noise that is based on the inaccuracies when measuring, and this is called the measurement update. The time update step is provided on the left, which can be used to provide the residual in the middle equation. The residual is then multiplied by the Kalman gain, given by the equation on the right, for updated estimates on the current state. This model is limited to linear models, so the rest of the Kalman filters that I will mention are adaptations to expand their use to nonlinear systems. The next Kalman filter is the extended Kalman filter, or EKF, which performs a first-order Taylor series expansion of the dynamic and measurement models to achieve a linearized model that can be used by the KF. Another Kalman filter is the unscented Kalman filter, or UKF, which works by linearizing errors by propagating the Gaussian random variables using a deterministic sampling approach. The UKF uses a minimal set of sample points called sigma points to represent the state distribution and covariance initialized by the equations shown on the bottom of the slide. The last Kalman filter that I will go over is the cubature Kalman filter, or CKF, which uses a spherical radial curvature rule to compute multivariate moment integrals to address nonlinearities. Cubature points with equal weights are used to calculate state variable means and covariances that give nonlinear optimal estimates shown in the first equation. The second equation is used to propagate the cubature points, and the third and fourth equations estimate the state mean and covariance matrices respectively. Now we can compare the Kalman filters. The first table provides a basic comparison of these methods where the LKF can only be applied to linear systems, while EKF loses more accuracy with highly nonlinear systems, which does not occur for the UKF or the CKF. However, the cost of having to deal with less linearity restrictions is a higher computational burden. UKF and CKF are considerably slower, and this is shown in the second table, where the average computation per cycle of a system using the same language and processors show that UKF and CKF are slower than EKF, where the CKF is slightly faster than UKF. Below, we can see that for the given system, a 10-degree error in the initial condition takes longer for EKF to converge than UKF or CKF, and a 23-degree error in the initial condition makes EKF diverge. These results show that the EKF is the preferred choice for weakly nonlinear systems, while the CKF is the preferred choice for a highly nonlinear system, because it has the higher error order accuracy and is even faster than UKF. One application of Kalman filters is in satellite attitude determination. This is more popular than deterministic models because Kalman filters only need one observation vector instead of two, since attitude determination is a highly nonlinear model. CKF is a good solution. However, this method can be modified to an adaptive square root quadrature Kalman particle filter model to update the error covariance without requiring decomposition at every step. This application allows the algorithm to achieve a superior performance than CKF could alone, with the addition of particle filter to address the nonlinearities more efficiently. Another application is in predicting weather patterns. This model is much more linear, which is a good application of EKF that lowers the computational burden and allows for more accessible real-time updates. Another DBN method is a variation of clustering called a time series clustering. Clustering is a technique in data mining that places similar data into homogeneous groups without a preconceived understanding of the class grouping. So time series clustering is a specific type of clustering that is applied to a sequence of continuous real value elements. Time series clustering algorithms can be modified from existing clustering algorithms, or the data can be modified to be directly implemented into these clustering algorithms, called feature-based and model-based respectively. One problem encountered by time series clustering is low-quality clustering due to the inaccuracy of methods such as k-means, k-meanoids, fuzzy c-means, and ascendant hierarchical clustering, because they have heavily rely upon the quality of the prototype. However, while this requires careful implementation of the prototype, time series clustering is very flexible in which algorithm is used and how the data is processed, whether discrete or real, uniform or non-uniform, and series that are equal or not equal in length. There are many different applications for time series clustering. In microarray data analysis, this method allows for clustering homogeneous genes by functional role over time-dependent processes such as cell cycle development genes. Another application is in stock market predictions, where it can be used to improve analyst tools for short-term investments by using cyclic components to recommend stock trades to the user. Also, in MRI, time series clustering can be used as an unsupervised method that is more resistant to noise than other current methods when using an alternative correlation-based fuzzy out. The last DBN I will go over is the autoregressive model, or AR model. And the AR model represents a random process that has linear dependence on previous values and a stochastic term shown at the end of the model equation. A modification of the AR model is the vector autoregressive model, or VAR. VAR allows the AR models to be applied to model interdependencies among multivariate time series, using vectors as signals instead of single values with an order of p. The VAR moving average model is a modification of VAR, taking trends from shifts in mean into account, where theta is the coefficient matrix that accounts for the moving average. An application of VAR models is in carbon dioxide emission models, where they can be used to compare emission levels with economic growth. The advantage of VAR over alternatives is that it does not require the often inaccurate identifying assumptions. However, these models do have the drawback that is in lag periods, need to be adjusted so they are not too large, so that it is computationally inefficient, but not too low, so that the residuals are causing biased estimate. Future direction of DBNs will involve increasing the accuracy without a corresponding increase in computational power. This is being done through variations of the CKF that are making it 5th and 7th order accurate, with potential to raise it further. Also, applying newly developed deep dynamic Bayesian networks to real-world applications has potential to address this, as deep networks are further being used in statistical methods. Overall, DBNs allow us to have effective time course models and predictions, and there are a large variety of DBNs. And as I mentioned, in the applications of these DBNs, there are many different variants. So different real-world applications have different options in the method that they choose. This is the end of my presentation. Thank you for listening.